All right, this is part 3 of the video. Now that we have an equation, we want to just learn how to use that equation. It says use your equation from exercise 3 to predict the heart rate for a person who takes 35 breaths per minute after walking for 25 minutes. Well, remember our heartbeat is our, and we can go back and look at the data, but our breaths per minute is X, and that's in our L1, and our heartbeats per minute is Y, and that's in our L2. So we have to remember that breaths per minute is X. So, if a person takes 35 breaths per minute after walking for 20 minutes, now all the data is for 20 minutes, so we don't have to worry about that 20 minutes here. We just need to find this answer. So breaths per minute is X, that means that goes there in the equation. We have to find out what 2.4 times 35 plus 17.6 is. Now, we could just use our equation, or our graph, and estimate 35 there. So let's, just to show you, if our estimate didn't need to be that accurate, we could just find 35 on our graph right here. Then go up to the y-axis and find out where it hits, and it hits right there, hits the line right in there. So we could guess that this right here is about 105. So you can guess about 100, heartbeats per minute. But we might want to be a little more accurate with that, and we can use our equation to do that. By finding the answer to this equation. Y is equal to 2.4 times 35 plus 17.6. Now, if I have it in my calculator, I could trace my line. Right now I'm on the dot, so I need to use my down arrow to get on the line. I think I'm on the line now. And I could just follow till I get X is 35. And that's about right there, pretty close. So about 101 it says. I could just enter 35 since it's an input value on my calculator, and it'll take me right there, 101.6. Or I could just use the equation and do 2.4, that's my slope, times my input value, which is 35 beats per minute, or 35 breaths per minute, and then plus my y-intercept, which I believe is 17.6, and I get 101.6 that way also. Or you could also go to your table, and you could scoot down to 35 on X. Quicker way to do that would be go to your table set, which is second window, and just start your table at 35, and then go to your table. And we can see the value 101.6 there also. So there's a bunch of ways you can find the answer once you have the equation. All right, but basically we're just trying to figure out the answer to this equation when we want 35 breaths per minute. Now it says use your equation to predict the heart rate for a person who takes 100 breaths per minute after walking for 20 minutes. And so I need to do this, 2.4 times 100 plus 17.6. Well, that's 240 plus 17.6, and that's equal to 257.6. And it says, do you think that prediction is reasonable? Well, we know the more breaths per minute, the faster your heart has to be beating. The problem with this problem is that 100 breaths per minute is way outside of our data. Notice that our data only goes up to 44 breaths per minute, and so 100 breaths per minute is way off of that data. You'll always want to be careful about that. Your equation you made to fit this specific data from 16 to 44. So if we go outside of that data, and that's called extrapolating, you have to be careful. Equations are not necessarily that accurate outside of the data. They're way more accurate inside. and that's called interpolation when you're finding answers to questions. Like the last question, we found 35 breaths per minute, which is right inside the data, and that seems to fit pretty good. We got about 101 there. So you got to be careful about finding answers to questions outside of the data. All right, in this next problem, we're going to do most of this in class, but I just want to point out a couple things to you. These are actual winning times of women's 400-meter relays from 1928 to 2004. And if we just, in general, look at the times, you might notice that they go down. So women are getting faster, it seems. And what we want to know is, can we maybe find an equation to fit that data? Does it go down in a linear way? And the first thing you would do to figure that out is make a graph of it, a scatter plot. And you can see a scatter plot on the next page. Here's the scatter plot. And it does go down in a linear way, somewhat. And we're going to try and model it with a linear equation. So we're going to try and come up with an equation that matches the data. Now you kind of notice that a lot of dots are quite a long ways away from the line that just drew there. And in particular, there is one that is way away. And also notice down here that towards the end we're not able to get very close. So there may be more than one line that works good for this. In the early years, we could maybe come up with a line like that, but in the more recent years, we might want to have a line that looks more like that. Well, to help with this confusion, we're going to actually learn a way to use your graphing calculator to get that equation. Anyway, and you may have also noticed that there was this one dot up here that seems to be quite a ways away from the data. Right? That dot is called an outlier. And what you may want to do is get rid of that dot, that piece of data, because it's so far from the rest. It turns out that that piece of data comes from the year. Now, on this graph, the points are plotted as years since 1920. So that means 1920 is right here, and this is 1930. So the outlier is, looks like about 28 years since 1920. So if we do 1920 plus 28, that's 1948, which is the years right after the war. So you might think about why, what happened in those years in the Olympics, right around World War II. Anyway, so we're going to do this in class. We're going to use our techniques to come up with an equation. Now remember that this data on the graph represents years since 1920. So if we look at the data in the table, we're going to have to think of this first year, if we think of years since 1920 as 8 years since 1920. So 1928 minus 1920. So take the year minus 1920 to get the values that are actually graphed. So 1932 minus 1920 is 12. 1936 minus 1920 is 16. So 1960 is actually going to be at 40 on the graph, and I'll show you that one more time so you understand. If you go to 40 right here, that's 1960. And the reason that people did that is because it's easier to work with smaller numbers than to work with that whole year and end up having those years in your equation. Also notice that about the graph, that they put a little squiggle here. That means they cut off from 0 to 41. So they're just starting at 41, and those are times. There's no need to show all the times all the way down to 0. All right, so I'm going to go back to that other data and show you how to use your graphing calculator to come up with an equation, and then in class we'll do this problem with the winning times. But as long as I already have that data in my calculator. So the equation, just so you remember, here's the equation that we came up with, 2.4x plus 17.6. There is a way to let your calculator average the data in your table. So I have all this data in my table. I want to come up with an average of all that data. So, and here's how you do it. It's called a linear regression. So I'm going to run the linear regression for this. And to do that, you press, let me put the key press history so you can see it here. Press Stat, Calc. So you arrow over once, and it's number 4, linear regression, number 4. And maybe you recognize the ax plus b. A is your slope, and b is your y-intercept. So when I press enter, as long as my data is in L1 and L2, it's going to average all that data and tell you what the average slope is and what the average y-intercept is for all that data. So I press enter. And you see that the calculator thinks the slope should be 2.22, and the y-intercept should be 22.4 above. So 2.22 and about 22.4. So let's put that into our calculator in our y equals. Let's see what that looks like. 2.22 x plus 22.4. Just want to make sure that was the right one. Okay. Wrong button. Fix that. Plus. All right. All right. Let's graph it to see what that shows. And I'm going to shut off my graph. There's one way you can shut off a graph but not delete it is just to press the left arrow. Once, highlight equal, press enter, and then it'll just have the one graph. So there's the graph the calculator thinks is correct. And so it came up with the slope for you and the y-intercept. Now, you notice that I had to average the values that the calculator gave me. There is actually a quick way to get that equation into your y equals. So I'm going to clear both these down. So I've already run the linear regression, so it's in the calculator's memory right now. If you press, let me clear this so you can see what buttons I'm pushing. If you press the variables button, it's right to the left of the clear button. And then press number 5, which is stats. Then arrow over twice to the equation. And number 1 is regression equation. That's a spot where the calculator stores the last regression equation that you ran. So press enter. And if you're in your y equals, it'll put that right in for you. Then you press graph. And if your graph is set up, it'll go right through the dots. And you can see how the calculator averages out those data points. And then you can use the calculator's equation to answer questions. All right, that's the end of the video. Class tomorrow, you'll do some of that.